Right, so we are recording. Thanks everyone for being here. It's a tight time of the year, especially people working on papers for deadlines, etc. But we're really, really glad that Javier has time to spend with us in the next hour to tell us about all the work they've been doing in his group at the University of Catalonia in Barcelona. So he's been there for a while. I think you did your undergrad there, then you did some time in Brussels for a master's and some work in industry before deciding to return to a research degree at the University of Catalonia. And then since then, you kind of established your group. I'm sure some of you would have seen different types of papers, particularly on video object segmentation. I think we did one of the papers in the reading group. And some of you might also have met Javier in EPIC, where they were talking about the different versions of their work on scan paths. So without further ado, he's a very active researcher in general. They run a very interesting summer school on machine learning. And as a group, you will, wherever you go in the community, you'll see some of the graduates of this group somewhere around the world. So this is a group to watch, I would say, even for the more junior people in that group, because they tend by some magic to find really good career paths. So that is usually good mentorship. Without further ado, thanks, Xavier, for being with us, and we will look forward to your presentation.
Okay. Thank you very much, Dima, for this really nice presentation, actually. I really feel a bit flattered and honored. And thank you all for being here online, for your time. I know that we are all scarce of time these days. And for those of you working on CAPR papers, best of luck, I guess. So my name is Xavier Giro, and I will talk about some part of our research in the field of image and video segmentation with low supervision. And now I will develop a bit more what I mean with low supervision, which I guess is the most tricky term. First, I should mention that most of the work I will present is actually part of Miriam Belveyer, PhD candidate, but actually she already submitted her thesis report. She's about to defend and already working in Amazon in Barcelona, in Amazon Research Barcelona. Very small group they have for vision, but now at least there's a group there, which is pretty cool. I think I'll skip the introductions. Dima did an awesome job there. And I will just briefly introduce the rest of the team. So Miriam, you already introduced her. Then Victor Campos, he's doing a PhD, also about to finish. He is more related into deep learning and reinforcement learning without reverse words. So that would be like unsupervised, or if you want, self-supervised, because it's more trendy, reinforcement learning. And then Amanda Duarte, she's working on sign language translation. So she has collected quite a large data set on American Sign Language, and we hope to release it very soon. But today's talk, I will focus on this part. If you're curious about the other parts, I'll be happy to take questions on that as well, but I will focus on Miriam's work, which I think that it's the more mature and that can make a nicer picture. In our group, we also have something that's called industrial PhDs. And for that, so this means like people who are in companies, but they are following a doctoral degree. So we have Delia, who's working in Billings, who is working on semantic web, Eduardo Ramon on 3D reconstruction, which is also a very hot topic nowadays, and Andreu Girbau, who's working on video object tracking, I would say. And then we have like awesome master and bachelor students who are, of course, helping us all in bringing all this research forward. So let's get back into the topic. I'll talk about semantic segmentation and instant segmentation. If you are not really sure about what's the difference, basically the idea of semantic segmentation is that we are going to label all pixels with a class, and that's it. But when we go to instant segmentation, we are also going to differentiate pixels with the different instances of the classes. And maybe not all pixels will be labeled. As you see, there's a large dark area. Now we'll be talking about semantic segmentation, instant segmentation, because they are very tightly related tasks. There's, probably that there's this panoptic segmentation that kind of includes all of them, but the overall topic, it's on here. So the main motivation for the talk is that if you are going to talk in segmentation, you need to collect in a classic setup, let's say, lots of annotations to label many pixels, and that's very expensive. So what we want to do, what we have been working with Miriam, is trying to explore different supervision setups, both for training at inference. And that's very important because I'm going to make the difference between training time and inference time. So at training time, we have our deep neural network. We always work with deep neural networks. We collect our data, our images, our annotations. That's the very expensive part of the story. And now when we have our trained model, when we have a new image, of course, we had the segments. That's nothing new here. So in the first part of my talk, I will focus on fully supervised techniques, or nothing in low supervision regime. But our interest, what we have been trying to do always, is try to have architectures that you can train end-to-end. And that's since the beginning. I think that Dimas was mentioning that in EPIC I talk about scan path prediction, that was saliency prediction, and kind of our contributions that since then that we are very interested in models that we can train end-to-end. So if we focus at different supervision setups at training time, what we need to do, we need to collect the data and then to annotate it, and that requires expert knowledge or maybe it's crowdsourcing campaigns, but in any case, it's going to take a lot of budget. So in part 2 of my talk, I will really focus on trying to reduce this budget, your annotation budget. If you're a company, you're going to spend a lot of money there, and if you can reduce that, that's always very interesting. Then, so far I've talked about training, supervision at training, but now there's another kind of supervision which is at inference time. Okay, so that's what right here we have it in bold. So in general, in many tasks, when you run inference, you don't expect that any kind of supervision. In many of the tasks, like if I have an image and I expect to have the mask of the object, there's no supervision at inference time. But there are some tasks where you want to help the system. So for example, the non-supervised setup for video object segmentation is you have a video clip, you feed the video clip, and then you expect the model to discover the objects and track them through the frames. But I will actually talk about it because we have a model that managed to do that. Actually, the first model that addressed the task of what we call zero-shot video object segmentation in the first part of the talk. But then later, I will also focus in the case when we talk about one-shot video object segmentation, which means that at inference time, so forget about training, now I'm talking always about inference, we provide some supervision to the model of, in this case, under the form of a mask of the objects that need to be followed, segmented, and tracked across the frames. So, of course, in any case, even if it's only one frame that maybe you want to annotate the objects they want to track, that's still expensive, especially if you think about inference time, right? Because normally people don't want to really annotate anything at all at inference time. It's very costly and time consuming. So at the end, at the last part of the talk, I will talk about kind of weakly supervised approaches at inference time. And in particular, I will consider the case of what we call language-guided video object segmentation, which means like if I want to segment an object, I want a very natural interaction between the user and the machine. So I will provide a linguistic referring expression like skater with green jacket in the left to describe the object that needs to be detected and tracked. So that's going to be the last part. So I will focus in this third part. So in general, like the whole global idea of the talk is that we have two types of supervision. One at training, one at inference. And that in the first part of the talk, I will talk about having like full supervision at training. And then whether if I have supervision at inference time, then I will talk about one-shot video object segmentation. If I don't have any, I will talk about zero-shot video object segmentation. In the second part, actually, then I will move to still image segmentation, but I will discuss about how to find like trade-offs, okay, between the performance of the models at training time based on the annotation budget that we spent on the to collect annotated data sets. So in particular, we will try to reduce the amount of supervision at training time and still have maybe keep the same or improve actually the performance in segmentation at inference time. In the last part, I will focus on this part of video object segmentation. Again, at training time, this video object segmentation, all of this will be totally fully supervised. Okay, when we talk about video segmentation, but at inference time, you have like the three options, right? Whether you provide the mask of the objects you want to track, whether you don't provide anything, say just feed the video and let the model discover the objects and track them. And there's this intermediate part in which, like in a very natural way for humans with language to describe the objects that we want to track. And that's overall, that's the whole story that I will be talking about. And now I'll jump into the details of each of them, okay? Cool, let's start with the first part in which we focus on video instance segmentation, actually, video object segmentation, which is kind of the same. And I will address two types of problems. One of them, it's called one-shot video object segmentation. Another one, it's zero-shot video object segmentation, which basically the difference is at inference time. As I mentioned earlier, our work since the beginning, I think that we have been dealing with deep neural networks is trying to have architectures that can solve tasks in an end-to-end manner. We tried because we think that's much faster, much cleaner, that's the way to go. And we observed that, okay, since the beginning, we had these ImageNet models in which you had an image, you feed it into convolutional network, and you will have like a label. And actually, there's a label, but actually there are many other semantic instances that appear in an image, like in this one, this famous one of the chubby cat. There's also grass, and there's also like a kind of stone, right? And our approach was kind of allowing the network to predict a different amount of labels, let's say, for this image. That would be like the general idea, but in kind of allowing it to condition the future predictions based on the previous predictions. So inspired with the works on language processing based on recurrent neural networks, we thought that this might be an approach that not for image classification as this example that you see here, but actually we applied for instance segmentation. So given an image, what the first step that we took is we feed that image into a convolutional neural network encoder. So this is totally common. You only feed the image once, okay? And then at decoding time, what we do is you decode step by step the different masks of the object. And when there are no more objects to discover, you just stop. So that's the classic setup for language. And we got this inspiration from the research we have in our university that are the link in translation. So what is pretty interesting of this is that notice that compared with many other works that like state-of-the-art works that doing object detection or segmentation, all these works are basically in the end they have like millions of candidates, and then at the end they filter out. So there's a post-processing step. Maybe you have heard about this super famous work, a recent one like called Dieter, that kind of takes this idea, not using RNN with transformers, but it's kind of a similar motivation. We don't want to do any post-processing. We just want to solve the problem. And actually by doing that, we allow to condition the predictions at time step t to condition the future predictions. So this is the first model that we presented called RSys, in which we have the image here and we decode the different objects, the different masks, classes, and confidence scores for each of the objects. And the decoder was RNN actually was a convolutional LSTM. I think I have a slide later with the details. Okay, yeah, we had it here. The encoder was a ResNet 101, and there were like some residual skip connections, like a kind of a unit style, but then the decoder, there are like comp LSTMs at different spatial scales. And here you will have the segmentation branch. And then here you have a stop branch. Basically, that's That's a branch that will tell you, okay, there are no more objects to discover there. And actually there's a classification branch and another branch that actually we didn't put in the model at the end, which was a detection branch. So it was also trying to have a multitask setup to predict the bounding boxes. Okay, I think I can skip this. So based on this first work that we have, it's called RSys, recurrent semantic instance segmentation. So that's what we have. We say, okay, now that we can discover the objects that we can find in an image, what it will be in video, right? Because now in video, there are different objects, but we also have like a sequence of frames. And that was the idea of our model that I guess that's what Dima was mentioning at the beginning that you check at some point in your reading group, that is called ARBOS. So
yep.
Now, okay, great, thank you. So probably you already know about it. So here the idea is that if we have the task of one-shot video object segmentation, means like I have one of the RGB frames annotated with the objects instances that I want to track. What I want to do is to track them through the video sequence, but that's very expensive, as I mentioned earlier. So there's this other approach of zero objects video segmentation, which you have nothing, you just feed the video. But as we had RSys, because RSys can discover the objects, that the part of discovering the objects, it was kind of solved, okay? Not state-of-the-art results, so don't try to compare us with faster CNN, but it's the idea kind of works, and it was doing interesting tasks. So what we do then, when we have a video sequence, we feed the RGB frames, we extract the visual feature for the image, and now at the decoding step, if we only had one frame, this would be like RSys, so that different time steps we discover the objects. And kind of the nice idea like of ARBOS is that in order to let's say track or do the re-ID of the object in the next frame, that's straightforward, because the only thing we need to do is to take the state of our RNN and feed it into as the next state, feed in the next state for the next time step. Okay, so the state of the RNN that has discovered the horse here, you feed it into for the next time step in. So this will be like real time. This will be like spatial sequence, so temporal sequence, spatial sequence. With just the state of the RNN, the predicted mask will be related to this other object. If you have ever work with object tracking, actually that's one of the big issues, because in many of these approaches, what you do is you top the objects on each frame, and then the challenge is just to do the re-ID, so to connect the objects that you have found in different frames. In our approach, this is done naturally, because the state of the RNN that has discovered the object is already the initialization for the mask of that object in the next frame. So that's a basic idea of ARBOS. And okay, I already mentioned this. And we tried, I think it kind of changed actually in terms of low-level architectural applications. We discovered that our model works better when, in addition to the state of the RNN, you also, so that's the state of the RNN goes through this branch, these arrows over here. You see that these branches, could be the state of the RNN, but we also feed the mask of the previous frame, which is something that I wish that didn't happen, but performance was better. But I guess that's one of these things that we are actually discussing. I think that yesterday I had a discussion again on this, because we are trying to improve it. So what we saw is that basically that by having the S would be spatial recurrency and the temporal recurrence, when we combine both, results are better. So if you compare these results, means the ones that you have above it's better. So having both recurrences, it helps. Then, okay, that's what I mentioned already. And then this plus here, it refers to some curriculum learning, which means like how we feed the training data into our model, how it learns. And maybe you have, that's something that, again, people in language have explored quite a lot for recurrent neural networks. So inspired by them, we thought, okay, maybe it would be better if we start training with have a few epochs by using the ground truth mask when as coming from the previous. So if you remember, yeah, here I have like this mask that was being fed from the previous step. So we compared what if we feed the previous mask that was predicted from the model or from the ground truth, because we always train in a fully supervised setup. And okay, by having this curriculum learning, I think we had in this model, we have like 20 epochs training with the ground truth mask, and then 20 epochs training with the mask that were predicted by the model. We obtain like some extra gain. And now I'll get back to this curriculum learning because we have some open questions here. This particularity of Arbos of our model, that by just, let's say, feeding the state of the recurrent neural network to the next time step, you already kind of have the prediction for the same object. You need to find do any matching. Actually, that makes it very fast at inference time. Okay, so that's a model that inference time it's pretty fast because you don't need to do any re-ID at all. So at least at that time, that's already like 2 years, I guess. That was much faster. And actually, in this field, there are some models that's called online learning models. That means that what they do is like you have one-shot video object segmentation. What you do is like for the reference frames, you kind of overfit to that mask, and then you do the inference. So we are not doing this at all. Okay, I think that's fine. Yeah, inference time, that's the important thing. If it works, yeah, there's a qualitative result of this work. Okay, 25 minutes. So this one-shot video object segmentation, we provide the mask for the first frame, and then we distract across the rest of the sequence. Okay, I think we can move it. We also, at that time, we were also, as our model had the potential to discover the objects, we also kind of were the first one trying to look at these data sets of video object segmentation and discover the objects and track them. So results, they are much, okay, video is not playing, graphic is not showing, so that's okay, no, that's what I expected. So the results, the performance drops, but at that time we were the first ones that trying to address that. So it still was an interesting point. But the performance here, you have like the performance for the same data with one shot, and you see that we got the decrease in performance. Nowadays, things work much better. Okay. Then, if you remember, when I was in this slide, I said, and I put some emphasis, like we had this curriculum learning. Like when we do the training, first we use the ground truth mask and then the predictive mask at inference. And that's an issue that we explore later and with some results that we didn't expect. And if I had 1 million students, we'll be still looking at them, but we don't have any now. So what we did is with another student, we took the same model and we use a different data set. And I think that's kind of, it's very important here that the set is on autonomous driving. I think that kind of makes the difference. And our research question was, okay, so what this is a good approach, like what we did in Arbos, that we tried that it worked better. Like, is there anything better we can do than having 20 epochs with the ground truth mask and then 20 epochs with the predicted mask? So here, that's the scheme that I was describing earlier. If they give us this object that we want to track, the RNN makes this prediction. So what do we fit at the next time step? The predicted mask or the one from the ground truth? Because this, again, is training time always. How should we train that? And we explore like different approaches of what we call scheduled sampling. Actually, we try different things, but I will just only highlight this one. Here, these figures, what they show is the probability of using a ground truth mask throughout the epoch. So here you have from 0 to 40 epochs, and this is the probability of using ground truth mask. So actually what we did the other time was using first the ground truth mask and then the prediction, right? Yeah, okay. And I think I just remember that there's a problem with this slide. So actually our results that we found is that what we did for this data set, it was exactly the opposite. So the results that worked the best, they were, so instead of being first I used ground truth and then the predictive mask, they were for this other data set, Kitty Mott's data set, it's called, best results were by using first kind of the predicted mask, okay, and then at the end of the training period, the ground truth. And at this point, we have many hypotheses, but no explanation. But if you are curious with that, and you're working on any of these related issues, we are happy to discuss. And there's a problem with the slide, so don't look at the slide. Okay, so just to conclude this first part, with Arbos, we managed to have a model, that deep model that was end-to-end trainable. We managed to solve zero-shot and one-shot PD object segmentation. And at that time, we were the first ones in addressing this task. And okay, and the results, they were kind of competitive in terms of accuracy, and especially they were really fast. And also we had this study on curriculum learning that actually we presented in the Women in Computer Vision last August. And actually the student there is looking for a PhD, and unfortunately she doesn't want to stay in Barcelona. She wants to move around, so maybe Dima wants to speak to her. Let's go for the second part, semi-supervised learning for image segmentation. Now let's forget about videos for a while. We'll go back to videos later. And now we focus on still images. And our goal is going to be to reduce the supervision at training time, okay? And hopefully, so in the other, or in other words, like having a good use of our annotation budget. Okay, so basically what our conclusion of what we think, and I think that you have seen we have all seen many papers lately, is that using semi-supervised or weakly supervised methods, that's a good option. It's a good approach for having a smart and efficient use of our annotation budget. And I know that there's all this, of course, this interest on totally unsupervised methods, but semi-supervised methods are performing really well, and maybe they are a bit more straightforward, like collecting a few labels. It might be really feasible. So we'll focus first on semi-supervised methods. This part has two subparts. So let's start with the first one. So this one, it presents basis. So this is a pipeline for semi-supervised instance segmentation and semantic segmentation. We run both types of experiments. What got the best paper award in last year in a division workshop. So as I mentioned, collecting ground truth labels for segmentation, that's a lot of budget. Probably want to skip that. So here the idea is like, let's collect some data. So there is always some data collection, ground truth labels, that's always there. Train a network, F, and then when you have this network trained, and this network, I will call it the annotation network with these weights trained with the ground truth labels. Let's take more images, so different images from the ones that I have annotated. And let's predict labels. This is what we call pseudo labels. The interesting thing here is that these pseudo labels, they get for free in terms of annotation cost. There's some computational cost, of course, but not in annotation. So from annotation perspective, they are free. And now, once we have our ground truth labels and our pseudo labels, let's put them all together, mix them all together, and then train a network that we're going to call the segmentation network. So that's going to be like the final goal. Our final outcome is this one. That's the one we are interested in. And see if by having generated these pseudo labels, that helps. That's kind of the research question. Okay, and the answer is that yes, that helps, and we kind of quantified how much it helps, and also propose some way to assess that. Let's get into the details of how it works. So we use with Pascal, what the setup basically what it considers like to have a few strong labels. Strong label means that we have the fully annotated image. When I say fully, means like If it's semantic segmentation, all pixels. If it's instant segmentation, it means like all the objects in the image, and then lots of unlabeled data. Everything from Pascal. So we then, at this point, we didn't do anything new in terms of architecture. We took off-the-shelf DeepLab3 for semantic segmentation, and we observe again, basically, what we have here in this plot is that by different amount of strongly annotated images, when we combine our the pseudo labels with the ground truth labels, that would be what's called the segmentation network. That's the second one. The performance of the segmentation network is higher than the performance of the annotation network. So I will just go back to so that you can really make the connection here. So the annotation network, we can evaluate. So the goal of the annotation network is to generate pseudo labels, but still we can evaluate the quality of these pseudo labels. Of our labels. We can use this network at test time as well. So what we do is we compare the performance of this network. Maybe it's easier if I say compare the performance of this network. It's the same one, but of this with this other one. Okay. If I call annotation network, it's the same one here. And what we observe is like for the same annotation budget, because we are only using these ground truth labels, the performance of the segmentation network is better than the annotation network. Okay, that's what you have here. Actually, there were some words that had already seen that. Basically, our contributions were in terms of evaluation, and we also were comparing. So we propose a common evaluation paradigm for both semantic segmentation and instant segmentation. So as I mentioned, we also ran this for instant segmentation with similar conclusions. In that case, we took ARSYS, our model, for evaluating the task of instant segmentation. When we compare with other works on semantic segmentations, and always, so we focus on low annotation budgets. Okay, that's also important. So we saw that our work in terms of the trade-off between annotation and the quality of the segmentations, it was over the state of the art for semantic segmentation. And here you have like some qualitative results. You have first column will be like the input image, let's say, and then A200 and S200, that's refers to the output of the annotation network, and S refers to the output of the segmentation network. So you can notice that the quality it's slightly better because it's not a giant increase, but it's better for the segmentation network than for the annotation network. In this case, when I write here 200, it means that we use 200 manually annotated images. So that's the kind of quality we obtain with DeepLab3 with 200 annotated images. If instead of 200 you use 400, quality improves. You always need to look at the results, like, well, I guess that compare annotation with segmentation network. That's the kind of experiment we run, and with 600, that's even better. So
how many pseudo-labeled images are there in each case?
So how many? Sorry, pseudo labels. I think it's always the same. I think that this works by heart. I would say around, but maybe I'm totally wrong.
Don't worry. I think there is a.
Yeah, it's a figure. Maybe it's, but I don't know. I would say maybe 1,000 or 3,000, but I really don't remember. It's kind of a setup that everybody is using for that. It's on this range, but it's like the training data set at the end, it's always the same one. It's just that you have more or less portion of strongly annotated images.
Mm-hmm. And there is a question from Will on the chat is, so that both networks are trained for the same task. You just train one with label data only, and then use that to generate pseudo labels to then train the final network in a bootstrapping manner? Question mark.
I think so. Yeah, bootstrapping means that you use the data that you predicted to train your model. If I understand in this way, yes.
Yeah. Mm-hmm. But you just don't make a distinction, right? Your training segmentation doesn't know which one is ground truth or which one is.
No, here, no, you just mixed everything up. Yeah.
Great.
Yeah, thank you for the questions. here already. Yeah, and then for the other task in segmentation, so it's better than other words, not than this one. But I don't remember what Miriam told me about this one. I remember there was a drawback, but I don't remember by heart. Maybe it's something related to computation, probably. But I'm not sure. You should read the paper if you are very curious about this one. No, actually, I remember. She always says that we focus our work in very low annotation budgets. Yeah, that's what she tells me always when I say, but what about this one? And then she tells me, no, but we are interested in this one. Okay, so that's our work kind of focuses on that. What's the time? Yeah, I think I will skip this part because I don't need it. No, I don't need this part. Okay, then on this research line, we had another work in which basically what we did is we wondered, okay, when you are doing this annotation of ground truth labels, which ones you should annotate. It's kind of an active learning for you. If I say like we kind of address the problem of active learning, but we only did one iteration, so we didn't do there was not many active learning loops. So basically when we annotate the ground truth labels, the selection was kind of random. In our experiment, we say 200, and then we took 200, and that was one run. And then I think Miriam ran experiments like 5 times. So there was quite a lot of computation. So we try to improve that and having like a smarter choice of which images should be labeled if you want to be very efficient with a fixed annotation cost. So what we did here, so we use a slightly different setup that I skip, but so just the idea that these are the slides that I skip, but the idea is that now we are using also weak labels in the sense of semantic labels of the objects that are there and how many they are. But for the story I want to explain, it's not important, okay? But if you read the paper, you'll see that we are using a slightly different setup. So what we are going to do is, we have our label samples that goes into the annotation network. So this will be like the ground truth. It will be like what we did in the previous step. But now, what we are going to do is we're going to predict the quality of the mask, that's going to be like the new part. So the annotation network, when it generates the pseudo labels, it generates a pseudo mask, but also how confident the network is about the quality of those masks. And that's going to be our guiding signal to choose which are the images that we are going to actually annotate as ground truth we did experiment with one loop, okay, of active learning. So it just when we fit the image into annotation network, predicted the mask quality, and then based on this quality, we chose which other images to annotate, and then we did one loop. So that would be the whole pipeline. With the quality, we select which images to annotate. Let's say human annotation. Of course, we use in Pascal. We already had that, and then we fed it into the annotation network. So that's again the same idea, but with a figure. So when we have an image, in this case, as I mentioned, we had the weak labeled, but I think that doesn't change much. We are exploiting this as well. We have the mask and the confidence. So yeah, this very quickly, like kind of the basic conclusion that we obtain is that, or that our results show that once you have this confidence, the best option was to pick, to choose images for which the confidence was in the middle range. So if the annotation network, so the one that generates the pseudo labels, is very confident about the mask that it's generating, like this range. So that's already learned by the annotation network. So there's nothing new to learn from it. So it's better not to use them. It's better not to annotate these images with human labels. If the confidence is too low, then probably they are too complex, or maybe they are not to representative for your data set. So just remember that we are working on Pascal data set, okay? And you can argue that maybe there's a data set bias, but if we assume that data is representative enough, I think that the claim is valid, and that the best results we obtained were when annotating images for which the annotation network was kind of so in the middle range of confidences. Here, okay, here it shows like the gain on quality with dash line. You see the results with the when we use the annotation network guided with the quality of the predicted mask, while with continuous line you see the random selection of images. So there's still again and again, it's always trying to do the best with fixed annotation budget. Cool, just to conclude this second part, we propose this mechanism of quality. Actually, I didn't mention that, but this confidence, actually what we are trying to do is to predict the intersection over union. This is a metric which is very popular for in segmentation, and that's something that we can compute, because we at training time we have the random labels of all the images. So we can train a network to predict the intersection over union of its predictions. So that's something that can be done. I think we got this idea from an ECCB 2018 paper. I think they were doing that for bounding box proposals in another field. I don't remember what application, but we got the idea from another paper of predicting the quality of your predictions to do something else. I would say that's a story. And this strategy outperforms a random selection. And as I mentioned, like the best samples, there are those of kind of average quality. That takes us into the last part of my talk, in which I'm going to talk about our most recent work on language-guided video object segmentation. So now, again, just to put everything in context, we are using fully supervision at training, and now we focus at inference time. What we do is we reduce the supervision at inference time. So now instead of providing the pixels of the objects that I want to follow and track, as that will be the case of one-shot video object segmentation, now we are providing a language description of the object that we want to track, segment, and track. This actually discover, segment, and track through the video frames. So that will be one video shot. That's too much budget. Then we talk about zero-shot video segmentation. Performance was lower, so kind of in the middle, there's this language-guided video object segmentation. In this work, what we did, so actually our work, this work, most of the work is on data set analysis, so don't expect any novel model here. We took off-the-shelf neural models, but we really look at the data sets. That was a huge work, and we propose improvements on the data set to better understand the task. Okay, so just to make sure that we are on the same page, this is the task that we will try to address. So if you have an image and a language query, like for example, Mar on the left on screen, we would like to have a mask on the object. Not sure if you see that this here now it's green, while here it was blue. So that would be like the mask with some noise over here. But if the referring expression is main guy on chibi, then we would like to have this kind of mask. So these are results from our model, right? Or woman in blue, that would be like this lady over here, guy on right, this highlighted in green. That's our goal, okay, for video. So what we realized when we started working on this is that the existing data sets, they had limitations. And so we try to improve these existing data sets by first looking at if they were easy or not, if the annotations were correct or not, and also like trying to categorize what kind of information they are providing. So first, we detected that many of the existing data sets for what it's called referring expressions, they seem to be trivial. So we're trying to address a task in which the language is helping, it's making a difference in in solving the task. So if we have this kind of video, okay, I know it's a still image, but there's a video and the referring expression is jacket. Okay, there's only one cat here, so that's not what we are trying to address, right? Because there's only one cat or there's only one ball. So we want to have situations like this one, in which there can be confusion. Like in this case, there are like two men, and or if you think about the class person, there are like two people here. So that's a kind of problems that relate to referring expressions, where the language is really making a discriminative on the task. So we found that existing data sets, many of the, let's say, language expressions, they are not even referring expressions, because referring expression, there's need to be a disambiguation task. They were trivial. Some others, they were non-trivial. That would be a good one, like the largest elephant for the red one, the green elephant for the one on the right. Okay, so here red and green do not mean correct or wrong. They mean you should do the mask with the match with the mask, or just not a referring expression like what I mentioned. Or sometimes there were actually like wrong annotations in the data sets. So we did analysis on dataset collected for Davis 2017, an actual a 2D dataset, and we saw that actually there were many problems. So that the right problem should be the blue one. So you can see that this dataset, they were not fully useful for the task we want to explore. So we kind of annotated, and also we provided we labeled the referring expressions if they are related to appearance, to location, to category, or especially like some categories for video, because we think that these are data sets for video. So we here you have the distribution of the kind of different expressions that we find in these data sets after our categorization for Davis and H2D now. So for H2D actually. And once we had these annotations, and we could take an off-the-shelf model. Actually, we had this model RefBoss, but there's nothing really new here. We use the encoder of DeepLab3. We got the language feature from BERT. And I think we're concatenating, if I remember well, the features to fuse them. We use these two data sets, Davis and actor action data set. And by running our model, which it's running frame by frame. That's when I say that there's nothing new in the model here. That's one of the reasons. So with the state-of-the-art models, we managed to improve the previous results on these data sets. And yeah, I think that's for Davis, the same story. So it's the same story as the other data set. Here there are some qualitative results, and we also managed to improve the state-of-the-art with this basic setup for model. Just to conclude, actually, so apart that we are trying to have a better, a nicer model for the video as well part, we also think that the challenge of having data it's an important one. And we recently have been working on the generating synthetic referring expressions. So all the referring expressions that you see in these examples, they are generated synthetically. So by this way, again, that's zero cost. And what we did, we exploited a SyncGraph, which is that these are an existing tool that what it does is describe the contents of an image as a graph with the instances and the relations that they have. And based on that, we feed that SyncGraph description into our handcrafted rules. They are handcrafted rules. I think there's nothing neural here. And it generates, we can have like many referring expressions and increase the data set for training. And we observe like some gains on that. I think there's like some video example, a big man on the right in black jacket. Okay, that's one of these examples that it's not spectacular, but okay, it still does something. And we observe like gains when using our synthetic data. So just to finish, we have ResBoss. This is a model that it's nothing really novel, but it's very competitive. Actually, I only talk about video, but we also have experiments on still images. So, and the code is already public and available. You can use it if you want. We propose a categorization for referring expressions and augment actually, we also collected new ones. Actually, I forgot about that. We'll take new reference expressions for the H2D data set. And we analyze these current benchmarks, and we think that there's still like that the new data we proposed, it can help into solving the task. And I think that would be it. I probably can skip this part. We are now, just in case probably you're going to ask, what are we trying to do now? Well, I guess that as everybody else, we are trying to incorporate transformers into the architecture. And for the annotation part, I think we are not working on this anymore, I would say. And for the language part, again, it's kind of related to the first one. We are trying to really have like more exhaustive experiments that we can show and publish, showing like the gain of having the synthetic data set, especially, and also hopefully trying to improve the performance on the architecture as well. So that would be it. So thank you very much for your time.
Very much for the detailed presentation. We have 7 minutes for questions. I think you can either ask us a question or write it on the text, and I'll start with one that is kind of nagging my head. So for the bit where you have these easy pseudo labels and then medium threshold, say, pseudo labels.
Yeah.
Why did you exclude the easy ones? What's the motivation for excluding them? Did they harm the performance?
No, the point is that, yeah, okay. I think I get the point. So the point is that, okay, I'll share the screen again. And I guess we are talking about this part.
Yeah, exactly.
So the story here is that with these scores that we get here,
yeah,
we are going to select which images we are going to annotate with a limited annotation budget. So if I pick easy images, that's going to be kind of wasting my annotation budget.
I see. I thought these are the ones that you included in the, what Will was calling the bootstrapping. So
no, because these are, okay, that was in the previous part. So yeah, I let me go back here. So the answer is no, but I'll try to explain better. These are in this part, in the active learning part, it's like going back, so I generate the pseudo labels, but I look at these scores, and then I choose which images I'm actually going to annotate, and that fit into the first network, okay, now I need to scroll a bit, fit into the first network.
Understood. Yeah. And I think the second question is, for Arvos, did you try at any point in time a bidirectional RNN? Is it something you discussed and excluded, or?
Oh yeah, discussed, but I mean, yes, it's discussed. It's probably going to improve performance, but I guess that Miriam wanted to do something else, and nobody wanted to do that. And we thought that, okay, if there's a gain there, that's nothing that spectacular, but it should improve performance totally. Based on any older literature we have read, it should. So in particular, yeah, I guess that would be the story. Probably it's more like probably on the agenda of Miriam. I'm not sure what happened between the submission of CPR and the acceptance, but maybe she was an internship and she wasn't able to put that in the camera ready, probably.
Good. Any other question? Yeah. Go ahead.
Xavier, it's Majid here. I work with Dima in the computer vision group.
Hey, Majid, nice to meet you.
I guess I'm really asking a question because I can sense there are not many more questions coming. So I thought I'd think of something to ask you and maybe just get some idea of your experience in terms of the annotation work that you've done. Now, I guess it's in two parts. I appreciate that you are using weak labels, but how would the work extend if you were going to have pixel level, strong labels, pixel level kind of segmentation that you wanted to do? And the reason I'm asking this is because often you can get situations where, for example, in medical image analysis, you might have even experts disagreeing on how pixels should be labeled. Maybe, you know, the disagreement over the shape or size of a tumor or whatever. So I'm just wondering, have you had any experience of that, and how did you deal with it? And then also in terms of stronger labels and more pixel level segmentation, how would that extend? How would your work kind of extend into that domain? Is that too much? No.
I'm not sure. I'll try to give my best answer, I guess. So I'll try. Okay. So first, the part that I skip, that you just mentioned, that that maybe you might have been interested. Of course, it's in the paper, but what we were doing is this thing. As weak labels, we had a counting on the objects that we had here. So if there are like two sheeps here, it would be like sheep and sheep. Yeah. Okay. So I don't know if you can have like two tumors in a medical imaging, or if you can have more than, if you want to explore weak labels related to the ones what we have, they will be weak. Related to what ones we have, they will be weak in the sense of counting how many of whatever you are looking is there. And in our model, it's pretty good at, it's kind of well suited for counting because it has this recurrency. Then, but you were talking about strong labels and disagreement between the annotators. I have never addressed this problem, I guess. But yeah, I guess I mean, I can probably everything I can think about. It's very obvious. Like, okay, just put everything in the model and that's it. At training time. I guess in medical imaging, for you it's very important. It's all these active learning setups, because I assume that it's super expensive to have some trained annotator to look at that image and start painting pixels. That can be a nightmare, I guess. And maybe what they do is probably like you show some results, and maybe they will say that's correct or that's false. I guess that would be like what they are willing to do, and maybe with that helps you a lot with that. But yeah, I'm sorry, but I think that I have never.
No, I was really philosophizing and wondering whether you had any experience, but it is kind of a separate problem.
Yeah, I mean, my experience here, it's like 3 or 4 years ago. Actually, this idea of the active learning that I show, the active learning part that I show, actually, it was inspired on a previous work that it was for medical imaging, and that we did with colleagues from Toulouse. And over there, the selection of which images they had to be selected, it was based on having so at inference time, adding a dropout, means like disconnecting some neurons at inference time. I think that multiple times for each image, and then if we saw like a lot of uncertainty at the predictions, then I think that we said that. I'm not sure what we were doing, but I think that if there was a lot of uncertainty, that was an image candidate to be given to the doctors to be annotated.
We have a final question on the chat before we cut. Thanks, Majid. Is from Will again. How would you decide when to stop decoding the masks? So what was the end of the RNN?
So at training time, so there is a stop. So there is actually a stop branch.
Stop, yeah.
There's a big stop here. Okay, that's one. But then if you look at the model, very small, there's here very, very small, it's written stop branch. Right. And at train time, the training is supervised, so we know how many objects are there, so we can train that there are no more objects. So it's exactly the same thing that people in language have been doing for ages. So we just applied the same.
Yeah, so you expect that the method will output the right stop at the right time.
Yeah.
Great. Thanks a lot for your time, for the detailed presentation. The recording, I will be sharing the recording with everyone as well, as Xavier. And thanks to Dan also for arranging the time and doing the communication. We will not be having one in a couple of weeks' time, thanks to CVPR Madness. I think the next one with Yanis Karantidis from Neighbor Lab will be beginning of December, and you'll receive the invite. Thank you very much. Stay safe, and hopefully next time we'll be able to have you here physically in Bristol in better times.
Yeah, I hope so. Thank you very much. It was a great time with you. Thank you for the questions.
Thank you. Take care.
Bye.